Hi, I'm Mark Allen. I'm very pleased to be with you today. I work at Alert Logic. It's based in Houston, Texas. A lot of our backend systems are written in Erlang, and that's how I came to be involved with the Erlang community originally. Anyway, I want to talk today about Sagas and also futures, which is something that is pretty well known in contexts that are not Erlang. And so I want to explore that concept a little bit in the context of a Saga in Erlang. And the final thing I want to talk about today is property-based testing. One of the things that's really great about the Erlang community is I think that there's an emphasis on correctness, and that is a wonderful thing. And one of the primary ways that we can build confidence that our solution is implemented correctly is by using property-based testing. And so I want to just briefly touch on some of the property-based tests that I've written for this particular library. So let's get started. The first thing I want to talk about is Sagas. Sagas are a Viking tradition. I'm in Sweden. I thought this was a good way to open. So let us discuss things in the way of Vikings. There's a paper. This paper was written by a computer scientist named Hector Garcia-Molina. He wrote this paper in 1987 and published it at Princeton. He's now at Stanford and is still working on all sorts of interesting research problems and areas. This paper describes four different types of Sagas, and the library that I have implemented in Erlang really deals with the first one, the backward recovery model. But there are three others, and I want to just briefly tell you about them because I think they're really interesting, and I think that there's room for multiple ways to solve this. And one of the goals I had in doing this talk was really to promote this idea of using Sagas in your production systems. So first of all, what is a Saga? We should really describe that. It's really a way to provide a transactional semantic in the context of things that are not necessarily databases, but they call on resources that are sort of out in your environment and may have failures. But you want a transactional semantic, so you either want all of those things to succeed or you want to unwind all of the things in your state back to the original point, right? You don't want to have partial failure. So some use cases that Sagas are really useful for are things like standing up cloud infrastructure. So if you want to create 50 compute nodes in cloud infrastructure and you might have partial failure on some of those things, you don't want to have a human or an operations person or yourself get paged at 3 in the morning to get up and unwind all those things by hand. You want some sort of automatic recovery mechanism or compensating mechanism. And those are the sort of things that Sagas can provide for you. So let's talk about the different types. The backward type is what I just described. So it provides that transactional semantic where you either move from state point A to state point B, and it's completely successful, or you unwind all the way back to state point A. And that does not necessarily mean that all of the things that happened in between during when you were processing that are no longer visible or didn't happen. But the semantics of it is that it's unwound, right? That you've taken compensating steps to get back to that original state. So that's one type of Saga. The next type of Saga is called forward recovery. And what this does is an idea that says, before we execute each step in our transaction, we're going to take a checkpoint. We're going to save the state somewhere persistent. And later on, if that step fails, then we can use that saved state to recover and try again, right? And eventually you're going to either succeed or you're going to fail. And so that's kind of the idea of forward recovery. So the idea here is that you don't sort of unwind all the way back to the beginning, but that you checkpoint at each step, and if you have a failure, then you can use that save state to try again. The next thing is a recovery block, which I think is a really interesting concept. A recovery block is the idea that there's multiple ways to do things. So in the Perl community, there's this idea called Tim Toady. There's more than one way to do it. And recovery blocks is kind of a formalization of that concept where if you fail doing it a certain way, then you can try again doing it a different way. So for example, if you failed calling a microservice with an endpoint that was in region A, for example, and it fails, then maybe you try with region B, right? You try some other region, say microservice, same state mutation in some backend system, but it's in a different region, so it's available, whereas in region A it was not available for some reason, right? Meteor strike, kaiju, something like that, who knows? So that's the idea of a recovery block. I think that's a really interesting concept, and I'm going to dig into that a little bit more later on in this talk. So the last one here is a parallel saga, and this is the most interesting concept to me, I think in the context of Erlang, especially with futures. And we're going to talk more about futures later on, probably in about 20 minutes, I think. And the futures idea is that you're making a promise, right? You're sort of assigning a token to a value which you hope will eventually exist. And in the context of parallel sagas, at least within this paper that I've cited originally, the idea was that you weren't going to have multiple parallel tracks of transactions executing, but that those things were not, they were all independently, right? They were all independent from one another. They didn't entangle. And all the things that entangled were in a single saga. So for example, the way I like to think about this is like you have a saga of sagas, right? So you have like this top level container, and then you have a whole bunch of executions that are going on that are independent from one another, and they're all executing concurrently and independently and asynchronously from one another. So those are the 4 different types of sagas that are described in the paper. Now I want to talk about my library, which is Sagas in Erlang. So really the big idea here is not a new one. How many of you have used FoldL? Oh yeah, just about everyone. All right, well, so this is the idea that we're going to use FoldL, but we're going to use FoldL sort of in the context of distributed transactions. So the big idea is that we're going to fold over a list of closures, and we're going to maintain some state that we pass between each one of those closures unless there's an error. And if there's an error, then what we're going to do is fold over a list of closures. And we're going to unwind all the steps that we took previously, okay? So let me show you kind of what this looks like graphically. So here's a saga that I've kind of represented, and you can see that I have 2 tracks of blocks. The top row kind of represents forward progress, and the bottom row kind of represents rollback progress, right? So compensating actions. If the forward box fails, then that lower box is the one that's going to compensate for whatever the top box did. Does that make sense? And then I have this arrow between forward 1 and forward 2 that kind of represents state, right? So this is our fold, and that arrow represents the state that we're transferring between each closure. And we're just going to roll through this, and we're done. We're super happy, right? Big blue happy face. Everyone is smiling. Yay, closures. We like them. They're awesome. All right, so, you didn't see the big blue smiley face. It was only on my my preview screen here, but anyway. So that was the happy path, right? That's the normal case. That's the case when everything happens exactly as we expect it to happen. And that does provide the semantic I talked about originally, which is you start at state A and you end up at state B, and there's no partial failures, and you don't need to compensate for anything. You just continue to proceed state to state to state to state, right? So you just accumulate all those mutations, and when you're all done, you report all the mutations back to the caller, and you say, hey, I was successful, and here's your final state, and here's all the here's all the execution information from each one. So let's take a look at a failure case, right? So what does that look like graphically? It looks like this, okay? Same setup. Top row is forward progress, bottom row is rollback progress, if you can think of it like progress, I guess. And again, the arrow represents state, and so we transition, and look, we had a failure. Boom. Something happened in closure number 3. Something didn't complete in time, or there was a timeout. Anyway, there was a problem. So what happens then? The library basically takes the list of closures that we were executing, and it switches to the bottom row. So it takes the state from the top row, puts it into the bottom row, and then we roll back, and we roll back, and we're done. Okay? Does that make sense? So are there any questions so far? Awesome. So I wrote this library called Gflow. Which I'm sure I'm not pronouncing correctly. If there's anyone here from Iceland, maybe you can tell me how to pronounce that, because I don't know. But to my American ears, it's Gflow. I'm sure it's probably something actually really different from that. Apparently, this is actual Icelandic Saga. Naming things is hard, So anyway, this library is on GitHub, and it's open source. You can download it, use it in your own projects if you wish. But the thing that I really wanted to talk about in the context of this was kind of the genesis of the library. I was at Strange Loop in St. Louis last September, and I saw a talk about Sagas. And the context of the talk about Sagas was kind of in the context of building Amazon infrastructure. So setting up a whole bunch of Amazon compute units, and they were using key distribution. So Amazon has a service called KMS, and what it does is it helps you build encryption keys and store your data at rest securely and all those sorts of things. And unfortunately, there are some rate limits on that. So if you call the service too many times, then Amazon says, nope, you've used up all your allocations for this period, and that was causing downstream failures. So if you didn't get a key from KMS, then you couldn't start EC2, and if you couldn't start EC2, then you couldn't do the compute job. And so what happened is they had all this compute capacity that had been allocated in Amazon that they were paying for by the hour, and it was never getting unwound, right? So it would just start up, and it would just sit there in the environment and run and run and run, which is really great for Amazon. It's not so great if you're being billed for it. And so he wrote this library. When I say he, I should talk about the guy who wrote it. It's another guy from Houston who was working on a contract, and his name is Daniel Solano. And he wrote this library in Scala that does Sagas. And I was like sitting in the audience, and I was thinking, that is a really cool pattern. We should have a library like that for Erlang. And I was like, surely someone's already written a library like that for Erlang. But no one had. So I wrote one. And it was kind of fun. And like I said, I think it's a really great pattern for interacting with microservices. So next I want to talk about some of the terminology in the library. So the library has sort of three big abstractions. The three big abstractions are on the slide. At the bottom level, going kind of from most specific to most general, we have an operation. So an operation is essentially the closure that I tried to represent earlier in my little box diagram. An operation is anything that you want it to be, and it can be of any length that you want, and they're executed sequentially, okay? A step is essentially a container for the forward closure and the rollback closure. So those get linked together, and they get put into a step, which is basically a container that has a name. And then steps get organized into a list that's executed serially in a transaction. So a transaction is the top level container for all of the steps. And steps, remember, has one forward closure and one rollback closure and a name. So that's kind of the organization of the library. The operation also has some extra stuff in it. It's a record. It's an Erlang record. It's implemented as a record. And the other things that it handles and does are things like timeout values. So how long do you want to let this closure run before you say that it took too long and you fail it? What state the closure's in? Like, is it ready to be run? Is it already run? Are we doing forward or rollback? Right? What is its type? It has all that kind of information in it. And then we organize it kind of into this row. Again, right? So this is the same diagram as before, but now it's organized kind of into the operational parts of it. You can see I have these brown boxes for each one of those 5 steps. The brown boxes represent a step, and the sort of outer blue big box, that represents a transaction. So you can think about the orange boxes being the operations, and the brown boxes being a step, right? And they're organized left to right, so they're executed left to right. And then the top level is this blue box, is the transaction itself. Okay? Are there any questions about this so far? Okay. So I've mentioned several times that I think Sagas are a great way to deal with microservices, but there are some implicit assumptions that you need to understand or at least accept if you're going to use Saga pattern in production. And there was a really, really good talk done by Katie McCaffrey, and she is really done a lot of work about publicizing Sagas and talking about how Sagas work in production. She's a software engineer at Twitter and has written a whole bunch and given a lot of presentations about Sagas. And a couple of the next slides are kind of inspired by things that she's talked about. But I have another friend, Tyler, who works at Fastly and has thought about how Saga is sort of in the context of messaging, right? So if you're setting up your Sagas, you need to think about what your messaging infrastructure looks like, right? Because you don't want to have failures that are sort of caused by brittle messaging. I think this is less of a concern for Erlang people than most other communities that I might talk to, but it's still something to be mindful of. Some other important, really implicit assumptions and requirements about Sagas are out there. So I just wanted to cover a couple of those. This is the most important one, though. When you're compensating for a rollback, it really cannot abort. You cannot have that thing fail. If you're a turtles all the way down kind of person, what's going to happen is that, at least in my library, if your rollback closure fails, that's it, game over. The whole thing's done, and you are going to have that partially failed state. I guess the question about that is like, maybe that's not the best choice. There are other ways that we could handle that, or there are other ways that you could implement that. But the easiest thing to do is just make sure that those compensating things don't abort. They just don't fail. You say, oh, well, that's not possible. In fact, Torben said that right before we started the talk. And I don't know, it may or may not be possible for that to be true. But in the general case, that's what really it's striving for, is that your compensating closures don't fail. The other thing that's really important about this is that if you're going to have a Saga where you're retrying things, then you need to have idempotent requests, right? You need to have requests that you can send over and over again without having a lot of state mutation in these services. So if you have something that's very stateful, then you need to take care about that. You need to be very mindful of what state you're changing and how you can compensate for that, right? So if you have a stateful mutation that cannot be idempotent, and there are certainly a lot of services like that, then you just need to be mindful of that when you're unwinding it. It may not even be possible to unwind, right? If you're assigning a user ID or something, maybe you don't want to unwind that. Maybe you just want to mark that thing as failed and move to the next user ID, in your database, for example. So that's one example. Yesterday I had a really interesting conversation at the tutorials. We were talking about Sagas, and I was talking about my talk a little bit, and we were talking about what happens if compensating transaction does fail. And I was like, well, it's kind of, we're done, there's nothing else to be done there. And he was like, well, what else could you do? And I was like, well, this is one thing that we could do. Right? What if instead of going from this failed state and rolling all the way back to the left, we had this? We had an arrow that just did a compensating action, and then it passed that state right back into the top box and tried it again, right? And you could try that a few times, and hopefully it would succeed. Maybe it's a transient failure. That was sort of my use case there. So if you call a web service and maybe it's overloaded or it's too busy, or the network had a hiccup or something, and it's a transient failure, you do a back off, like you wait for 100 milliseconds, and then you try it again. Maybe it'll work. That's not how my library is written today, but I think this is a really interesting, excuse me, a really interesting idea. So it's something I really want to explore, but I haven't gotten to it yet. All right, so the next thing I wanted to talk about was futures. So why does Erlang need futures? It doesn't need futures, except if we're going to have asynchronous Saga operations, then we kind of need to have something that's an abstraction that's useful in that context. And to me, that was a future. So I wrote another library called Criswell. And Criswell is a pretty simple and straightforward implementation for what a future is. And I'm calling them futures because that's what makes sense to me. So you think about a future in the context of something like Scala. Really what you're asking for is, I want you to perform this computation, but I will asynchronously look up the value, right? So go out and do this thing, and then later at some point in time I will resolve this value, and hopefully the computation will be finished and it will resolve to a value that is useful. But in the meantime, I don't have to wait for it to process. I can just dispatch this request and continue on my merry way, and asynchronously I will get the value out of it. So the way I wanted to implement this in Erlang was that essentially it's, again, closure-based. You take a closure and you assign it to a reference. The reference is stuffed into ets, and then later on, when that value and that computation is available, that goes into ets too. And then later, when you ask Criswell for the value, it pulls it out of ets if it's available, or if it's not available, it tells you, hey, this computation's not finished yet, so it's not available yet. And of course, you can have blocking, like you can wait for the value to show up, or you can just continue to compute and accept that it's not done yet. So the thing that's been a little bit confusing to me, and the thing that I'm still thinking about, and the thing that I would love to discuss with you during the context of the conference is, what are the semantics of this? What does it mean to have futures in the context of a Saga? So the idea of a Saga is that you want to have this transactional semantic. You want to go from point A to point B, and you don't want to have any partial failures. But if you have an asynchronous operation in that, what does that mean? So for example, if you had a step in my box diagram where you went off and you asynchronously computed something and you had a failure, do you just do the compensating transaction for that one thing? Right? And then what happens after that? You have a Saga then where not all the steps succeeded, but the Saga itself is done. And if you execute the whole Saga asynchronously, then that opens up a whole new can of worms, right? So I'm still trying to grapple with this and wrestle with it, and I don't really understand exactly how it's supposed to work in the context of a Saga yet. But the thing that's really interesting to me is that in the original paper from 1987, as I mentioned, there's this idea of parallelism. And that does delve into this idea of concurrency and how you're going to deal with asynchronous computation. But in terms of how you implement that, I think that's an open question, and it's certainly not something that I've cracked. I've thought about a whole bunch of different ways to approach this, and none of the things that I've tried really make sense to me at all. So if you have any bright ideas about this, I would love to hear from you. I'd love to hear what you think about how an asynchronous Saga might work semantically. So yeah, please think about that. You're all smart people, and I would love to harness your brain power. So let's finish up with talking about property-based testing. How many here are familiar with property-based testing already? All right, cool. So all of you kind of know what it is, or at least mostly know what it is. The thing that I think is really great about it is that it lets you test your invariants. So for example, one of the invariants I wanted to test for this for my Saga library was that if I have a forward-based Saga and it completes successfully, that all of the mutations in state actually happened, right? That it was completely successful and there was no partial failures. And so I wrote a property-based test that does that. And I just wanted to quickly mention, there's this nice academic history, which if you haven't read, maybe you should delve into. There's this paper, very famous paper, that deals with it called QuickCheck, and it's well worth your time. And of course, there's lots of implementations for different programming languages. One of the things I thought was really interesting was Thomas Arts talked about how to do QuickCheck in the context of Elixir at a conference in 2015. And there's a link to the video on this slide. And I'm going to publish the slides after the talk, so you can watch it if you like. But it's really great. So in Erlang, we're sort of blessed with a richness of implementations for property-based testing. There's the commercial QuickCheck version, which is fantastic. And there's also QuickCheck Mini, which doesn't handle Statum, which is understandable. There's also the proper library and trick. Again, sorry about that. There's the trick library that's also available. So the idea here basically is that we want to have generators that randomly generate values. And those are going to help us build up basic types. And then we can combine those in interesting ways and be able to test more complex generations. There's a set of macros that are available for each one of these libraries called let and such that let you control how those generators work and what sort of values they generate. And then finally, you want to test your propositions. You want to test your invariants. And those, again, have a macro that's kind of, that you set up a variable in your generator functions, and then you have a test function that feeds in that variable. And that is going to let you test all of your invariants. So currently, I have a forward-based, property-based test, and I'm working on one that has a failure, occasional failure. And I had a really interesting discussion with Thomas Arts this morning, which I'm very grateful for, about how we might implement a generator for that. And so I'm eager to explore that idea as well. So that's what I have to tell you about Sagas and the implementation that I wrote for Sagas. Here's a list of resources. All this code is available on GitHub right now. The Sagas paper is available at that link, and then there's a couple of talks from Katie that are really great, and then the slide deck will be published very shortly after the talk's finished. So I'd love to take questions.
Thank you.
Thanks.
And questions? One.
Thanks. In one of your really early slides, where you show the crash in state 3, and then you called the redo or undo function of state 3 there.
Yeah.
I guess you don't really get the state from state 3 in that case. You get the state from how it looked after state 2, right?
No, we get it from state 3 because what happens is that all the closures are dispatched into their own. We spawn a process for every closure that gets executed. So if it fails, there's a monitor that takes the failure message and goes back to kind of a temporary supervisor, if you will, that manages the whole Saga's execution. So the failure is isolated just in the context of that spawn, and the message comes back to the mini supervisor. The mini supervisor processes it and says, oh, I'm going to take the state that I have and feed it back into the rollbacks.
Okay. So, and is that the same callback that you use if you crash in this state or if you've crashed in an earlier one? Because I guess the message that you get in the callback will look a little bit different. I don't know if I made sense.
Yeah, I'm a little bit confused about what you're asking for.
If I'm crashing in state 3 and then I get called in the undo function of state 3, then I get one type of message. But if I instead, when I'm getting called back to state 2 there, when I go back all the way, I guess I do, then then I wouldn't get an error message from state 2. This is hard to explain.
So the way that the semantics work is that just to be really clear about it, the way that it works is that every closure spawns into its own thread, into its own process. Sorry, into its own process space, and there's a monitor on that closure. And if the closure fails, then that message comes back to the supervisor. The supervisor has a state stored inside of its loop that it's asking in the receive loop. And so when that message comes in, it says, oh, here's my saved state. I'm going to figure out what closure to execute next by taking the list that I have currently and reversing it, and then chopping off the parts that I don't need to execute. And then I'm going to take my save state and use that as the state to inject into the rollback. Okay, so then it would roll back from state 3 to 2 to 1 and then done.
Exactly. And then, sorry, I'm taking up every time here, all the time here. But in state 3 there, then I get the crash from state 3. But in 2, then I didn't crash in number 2.
You're asking why are we rolling back to state? Why are we rolling back the progress that we made in state 2 and state 1?
I like that. I understand why you roll back. I just think that with the rollback functions for those would look different because the state 2 succeeded, right?
Sure. But the idea is that you want to be able to. So the overall goal is that you want to move from A to B, and you don't want to have any partial failures. And if you do have a partial failure, then you want to unwind the whole thing. Yeah. So yeah. So the way that you would handle that is that you would have to roll back all of that. Yeah. But if you had not failed in earlier steps, the closure that you have to unwind that progress might be different based on the state that you get it. So when you're in those compensating closures, the state that is added to that function call has all the information about what the context is that you failed in.
Okay, yeah.
Does that make sense?
Like, yeah, that's what I wanted to get at. So you have different compensating functions. If I was crashing in this exact state, or if I was crashing in a earlier state, I guess the callback functions would have to kind of take care of that. Right? Yeah,
so a lot of this is up to the callback implementer. Yeah. There are a few sort of utility things that I provide. Like one of the things that the library offers is checkpointing. So if you're in the middle of a very long forward progress, you can take that partial state and send it to the mini supervisor so that it has it in case there is a failure. Then you don't have to lose any of that, right? So if you have an operation that has like 3 or 4 individual discrete parts to it, then those can all execute and you can checkpoint that progress. And then if there's some risky thing that you're doing that you think might time out or might fail, then you can checkpoint all that progress before you execute that if you want. Okay?
Cool, thanks.
Yeah, thank you. Thanks. Those are good questions. Appreciate it. Thank you.
Any more questions? Yes.
Just one here.
So one of the things, the properties of transactions is that you cannot observe what's going on in the transaction from the outside. Is this here the case too? Because it seems to me...
It's not pure. It's not a pure transaction. It's a transactional semantic, but it's not a transaction like in the sense of a database transaction.
Yeah. So when I follow up on this question, so if you have made a couple of changes, right, down your step.
Yes.
Somebody else has observed it.
Yes.
Will this other guy also be rolled back then? Because there could be dependencies, right?
Absolutely, there could be dependencies. The thing that is important to think about in the context of building a Saga is how you construct those dependencies, right? And my suggestion for that would be to defer all of the other sort of things that you want to have visibility into until the Saga is either complete or rolled back all the way. But it is true that you can see impure sort of partial updates and partial state and partial failures for outside of the system, right? So you can have a Saga that advances the state in these different microservices, and then you might have a compensating transaction that revokes that mutation, right? And if you are in that situation, then you need to be able to recover from that. You need to be able to do that. The way that you can do that is really up to your implementation, right? So to my mind, there's no way that I can think of that would really solve that within the context of a Saga, other than to see if the Saga itself completely succeeded or completely failed.
Thank you.
Thanks. Good question. That's a really important subtlety about Sagas is that it's not a pure transaction in the sense that visibility is not preserved, atomically. So external things that are looking at the states of things can see the mutations even before the Saga itself is completely finished. So.
Okay. Any more questions? No.
All right. Thanks very much.
Thank you.
I appreciate it. Thank you.